All right, today we're diving into something pretty cool, a new method that could finally turn AI into a trustworthy partner for real scientific discovery. And the secret sauce? It's all about teaching the AI the fundamental rules of the game, the laws of physics.
So let's just kick things off with a massive question. Could an AI design a better jet engine? Now, this isn't just some coding challenge. We're talking about pioneering new engineering, where failure isn't an option. It's pretty much the ultimate test for an AI in the physical world. And here's the kicker. The answer, according to some fascinating new research, is that even our absolute best AIs would probably fall flat on their face trying to do this. And not just fail randomly, but fail in very specific, predictable ways. We're going to break down exactly why, and then we'll get to the brilliant solution. Okay, so to really get the solution, first we have to understand the problem. And this is key. We are not talking about building a website here. Scientific software, well, it's a completely different beast, playing in a whole other league of precision and consequence.
Think about it like this. If a button on your favorite app is off by a few pixels, it's annoying, sure, but it's not the end of the world. But scientific software, it demands absolute mathematical perfection. We're talking bit-for-bit reproducibility, meaning if you run the same calculation twice, you better get the exact same answer down to the last digit. Any little error could lead to a flawed rocket design or a completely wrong scientific conclusion. The stakes are just so much higher. So researchers put today's AIs through their paces on a really tough combustion problem. And what they found wasn't just a mess of random errors. No, they saw a pattern. They were able to identify 4 distinct categories of failure that show us exactly why AIs have such a hard time with the laws of physics. The first failure type is fantastic. It's called an interface hallucination. This is literally where the AI, with all the confidence in the world, just makes up code. It'll write a line that calls on a function that sounds totally plausible, but it just doesn't exist. It's like citing a source from a book that was never actually written. And this is a perfect example from the actual study. ChatGPT tried to call this method int_energies_mass. Sounds legit, right? Problem is, the software library it's using, Kintera, has no idea what that is. It's a complete fabrication, so the code just immediately breaks. Now, the second failure is a little more subtle and, in a way, a lot more dangerous. This time, the code is syntactically correct, but the AI makes a completely wrong assumption about the physics it's supposed to be modeling. It's like a chef meticulously following a recipe, but using salt instead of sugar. All the steps are right, but the final result is just a disaster. Just look at this example from Claude's Sonnet. The model was tasked with solving a problem that happens at a constant volume, like in a sealed container. But instead, it used a formula that's meant for a constant pressure situation, like something happening out in the open. It fundamentally misunderstood the science of the task. The third failure is where things start to get really weird. This is when the AI's code spits out results that literally defy the laws of nature. We're talking things like calculating a negative temperature. But even worse is when the AI writes code that hide its own mistakes, letting the program just keep running silently with totally bad data. This piece of code from Gemini is a perfect and, honestly, a terrifying example of that. This try except block. It basically says, hey, if anything goes wrong here, just, ignore it, send back a bunch of zeros, and keep on trucking. For any scientist, this is an absolute nightmare. A silently incorrect result is so much worse than a program that just crashes. And the final failure class is all about the basic setup. AIs often stumble right out of the gates. They'll ask for configuration files that don't exist, or they'll pick the wrong scientific model for the job. They have this bad habit of just defaulting to whatever model was most common in their training data, not the one that's actually right for the problem they're trying to solve. So let's recap. We've got hallucinated code, bad physics, impossible results, and broken setups. The whole situation seems pretty bleak for AI and science. But this is where the researchers flipped the whole script. Instead of just pointing out the problems, they built a whole new way of thinking. Okay, the difference here is everything. The old way is what you could call code first. The AI just generates a big block of code, and then a poor human has to go in, write tests, and hunt for all the mistakes. It's like building an entire house and only then looking at the blueprints. The new way is physics first. Here, a human expert starts by defining the fundamental rules of physics as a series of tests. Then, the AI's only job is to write code that can pass those tests. You give the blueprints to the builder before they start. It's a game changer.
And the core building blocks of this new method are called unit physics primitives. Now, don't let the fancy names scare you. Think of them as the non-negotiable laws of nature, just translated into code. Simple rules like mass must be conserved or temperature can never be negative. The AI isn't just asked to solve a problem, it's commanded to obey these fundamental principles no matter what.
And this isn't just one AI doing all the work. It's a whole team of specialized agents. First, you've got the supervisor agent, who's like the project manager. It makes the plan. Then the code agent writes a few different versions of the code. A diagnostic agent comes in to fix any simple setup problems. And then, most importantly, the verification agent acts as the physics police. It checks every single solution against those unit physics rules. If a solution fails, the feedback goes straight back to the supervisor, who refines the plan and tells the team to try again. It's this constant loop of creation and verification.
So, all that sounds great in theory, but does it actually work? Well, the researchers set up the ultimate test, a head-to-head showdown. They took that same difficult combustion problem and gave it to every major AI model out there. And then they gave it to their new chain of unit physics system. The results are, well, they're just stunning. Take a look at this table. ChatGPT failed, Claude failed, Gemini failed. Even all the specialized coding agents and open source models, they all failed. Every single one fell into one of those 4 error traps we talked about. But the chain of unit physics framework, it passed. It was the only system that produced a correct, working solution from start to finish.
And when I say succeeded, I mean it got the right answer. This number you see on the screen, that is the correct ignition delay time for the hydrogen combustion problem. The system didn't just generate code that ran without crashing, it generated code that produced a verifiably accurate scientific result.
But the story doesn't end there. In fact, this is where it gets really mind-blowing. The code generated by the chain of unit physics system wasn't just correct, it was actually better than a solution written by a human expert. Just look at the runtime. The AI's code was over 33% faster than the humans. And you know why? The AI used a more efficient coding technique called vectorization, which is basically like doing calculations on a whole list of numbers at once, instead of one by one. It's a clever optimization that made a huge difference. And it was more memory efficient too. The AI's code used about 30% less memory because it found a smarter, more compact way to organize the data. So the code it produced was not only faster, but also leaner. And here's the crucial part. These performance gains didn't sacrifice any accuracy. The results from the AI's code were basically identical to the human expert's code with an average error of just 0.0031%. I mean, come on. It was faster, leaner, and just as precise. This all brings us to a final, really big question. This chain of unit physics idea isn't just a better way to get an AI to code. It could be a whole new model for how humans and AIs collaborate on science. By forcing the AI to respect the fundamental rules of the universe, we don't just stop it from making mistakes, we might just be unlocking its true potential. So what problems could we solve if we could finally trust our most powerful tools to never, ever break the laws of nature?